Prepare yourself for a shocking truth. The oxygen you are breathing right now, very likely, does not come from any land-based tree. Instead, this life-sustaining source comes from the vast ocean, produced by microscopic organisms so tiny that millions of them could fit into a single spoonful of seawater. What's even more astonishing is that most of us have never heard of these silent heroes. Are you curious to uncover this secret? Try asking anyone you meet. Where does the oxygen we breathe come from? Undoubtedly, the answer you'll receive will be quick and confident. From trees, from green forests, from plants, of course. The Amazon rainforest, often dubbed the lungs of the planet, is a prime example. Hold on, this isn't entirely wrong. Plants do indeed produce oxygen. However, this truth is so one-sided that it inadvertently leads to serious misconceptions. Because the familiar image you're picturing in your mind, vast, lush green forests as the primary source of the air you breathe, is fundamentally a mistaken notion about where the majority of this vital oxygen production actually takes place across our planet. In fact, between 50 and 80% of the total oxygen in Earth's atmosphere actually originates from the vast ocean, and not from the clumps of seaweed you often see washed ashore, nor from large marine plants growing deep on the seabed, but precisely from tiny microscopic organisms floating invisibly in the surface layer of the immense ocean. Creatures that are completely invisible to our naked eye, and without their presence, the air you breathe would fundamentally change. But before we delve deeper into these organisms, there's an aspect of photosynthesis that almost no one explains accurately. Often photosynthesis is presented in a way that gives the impression as if plants are some kind of benevolent, specialized factories, solely dedicated to producing oxygen for animals to breathe. It sounds like a great story, but this emphasis isn't entirely accurate. The true nature of photosynthesis, surprising fact. Photosynthesis wasn't designed to create oxygen. Instead, oxygen is just an unintentional byproduct. It's simply waste from the core objective plants are pursuing. Plants' ultimate goal is to capture carbon by absorbing carbon dioxide from the air. They break down that molecule, retain the carbon, and use it to build complex molecules, essential organic molecules that form their tissues, such as glucose, cellulose, and lignin, all the structural materials and essential energy sources they need to survive and grow. However, there's a problem. The carbon in CO2 is tightly bound to oxygen. To keep the carbon, they are forced to discard the oxygen. And the way photosynthesis gets rid of oxygen is by releasing it into the atmosphere. Interestingly, what you're breathing is actually plants' metabolic waste, a byproduct they expel while doing what's truly important to them, which is building organic carbon. However, this doesn't make oxygen any less valuable to us, but it certainly changes our perspective. We don't owe plants for generously producing oxygen for us. In fact, we're utilizing their very waste. So who is actually performing most of that photosynthesis on this planet? Not trees, nor vast rainforests. It's oceanic phytoplankton. Phytoplankton is a broad category including thousands of different photosynthetic microorganisms, such as bacteria, photosynthetic unicellular algae, and marine cyanobacteria. All of them share one common characteristic. They are microscopic. Did you know that right on the ocean's surface, where the brilliant sunlight shines, tiny organisms are diligently performing photosynthesis? They are so minuscule that they're invisible to the naked eye. Yet just 1 liter of ordinary seawater can contain millions of individuals. This entire vast ocean is teeming with these organisms, in numbers so immense it's hard to believe. And when combined, the entire photosynthetic output of these trillions of microorganisms, when aggregated, they produce a greater amount of oxygen than the total oxygen produced by all the terrestrial forests on this planet combined. The reason is actually very simple and lies in scale. The ocean covers 71% of Earth's surface. The sunlit surface layer of the ocean is a vast expanse, packed with organisms solely dedicated to absorbing sunlight and performing photosynthesis non-stop 24 hours a day, 365 days a year, in numbers that cannot be matched by any terrestrial ecosystem. And among those countless phytoplankton species, there's one particular inhabitant that deserves special attention because its story is truly extraordinary. It's called Prochlorococcus. This is a marine photosynthetic bacterium with a size of only about a mere 0.6 micrometers in diameter, making it one of the smallest photosynthetic cells we've ever known. You can't see it, nor can you sense its presence. No sensory experience whatsoever can connect you to its existence. Yet, astonishingly, it produces approximately 20% of the total oxygen in Earth's atmosphere. This single species of bacterium, one species, responsible for 1 out of every 5 oxygen molecules that enter your lungs with every breath. It is the most abundant photosynthetic organism on this planet. Try to imagine a staggering number. An estimated 10 to the 27th individuals of this organism are hidden in the ocean. That's a number so immense, it almost defies our imagination. In fact, the number of Prochlorococcus cells in the ocean far exceeds the total number of stars we can observe in the entire universe. What's astonishing is that this organism was only discovered in 1988, even though we've been breathing its precious oxygen. For millions of years, our very lives completely depended on it, without ever knowing of its existence until less than 4 decades ago. It completely eluded scientific understanding, not because it was rare or hard to access. In fact, it's present in every corner of the ocean, but precisely because of its incredibly tiny size. Traditional sampling methods completely overlooked it. Penny Chisholm, the brilliant oceanographer from MIT, unveiled this secret thanks to flow cytometry, which in essence uncovered a form of ocean life that all previous research methods had systematically missed. And that seemingly invisible something turned out to be the most abundant photosynthetic organism on the entire planet. We are breathing every breath thanks to an entity that scientists hadn't even known existed even when your parents were in their prime. This is a fact that truly astonishes most people when they first learn about it. Another shocking fact: mature forests, those that have reached equilibrium, are not net oxygen producers. Wait a minute, this completely contradicts everything you've ever heard about the Amazon rainforest, dubbed the lungs of the planet. Let me clarify. It's true that a tree produces oxygen during the day through photosynthesis. That's not wrong. However, the tree itself also continuously consumes oxygen through cellular respiration and its metabolic activities. Let's explore. Plants constantly harness energy from organic molecules. However, when night falls, they consume even more than they produce. And not only that, at every moment, countless bacteria hidden in the forest soil, along with fungi and insects, every organism present in this complex forest ecosystem continuously absorbs oxygen to sustain life. Even when a tree loses its life and begins to decompose, that very decomposition, which is essentially a form of oxidation carried out by microorganisms, also consumes a large amount of oxygen. Wood, which took decades to form through photosynthesis, now decomposes, returning to the atmosphere. A massive amount of CO2, and simultaneously consuming the very oxygen that photosynthesis previously produced. In a fully developed forest where everything reaches a perfect equilibrium, with trees growing, thriving, and decaying in a continuous natural cycle, the amount of oxygen produced by photosynthesis and the amount of oxygen consumed through respiration and decomposition almost reach an absolute balance. Therefore, the net contribution of a mature forest to atmospheric oxygen is virtually zero. So what truly makes forests incredibly important? It's their ability to store carbon. Wood, in essence, is carbon in solid form, absorbed and retained by trees from the atmosphere. An existing forest can store an enormous amount of carbon, no longer floating in the atmosphere as greenhouse gas CO2. This is precisely why deforestation has such immense significance for the global climate, but not primarily because it reduces oxygen production, but rather because it releases vast amounts of stored carbon back into the environment. However, our primary source of oxygen doesn't come from forests. Instead, it comes from the vast oceans. Imagine, 2,700,000,000 years ago, if you could set foot on Earth and breathe the atmosphere at that time, you would certainly die instantly. Not because that atmosphere contained harmful substances, but because there was absolutely no free oxygen. Our planet's primordial atmosphere then was merely a mixture primarily composed of nitrogen. Earth's early atmosphere, methane, carbon dioxide, water vapor, completely devoid of free oxygen. Remarkably, life still flourished, but it was anaerobic life which had evolved to survive without oxygen. And ironically, oxygen was a deadly threat. Then a historical turning point. Cyanobacteria developed photosynthesis, an oxygen-producing photosynthesis, releasing this gas as a byproduct, and they began to pump oxygen in enormous, ever-increasing quantities. For the anaerobic life dominating the planet, this was an extinction-level catastrophe. Oxygen, a highly reactive oxidizer, and for organisms that hadn't evolved defenses, oxygen was nothing short of poison. Cyanobacteria inadvertently turned the atmosphere into a toxic dump with their own metabolic waste. This seismic event was dubbed the Great Oxidation Event, and it occurred approximately 2.4 billion years ago. This was the largest scale pollution disaster in the planet's history, and astonishingly, it was caused by microscopic organisms, entirely unintentionally. They were simply performing photosynthesis. Most anaerobic life forms that existed at that time were wiped out. A mass extinction event triggered by a sudden change in atmospheric composition as oxygen accumulated to a threshold that existing organisms simply could not tolerate. The fortunate survivors were those species that had either developed mechanisms to adapt to oxygen, and these very survivors are the ancestors of all life on Earth today. You are here precisely because your earliest ancestors resiliently overcame the most horrific environmental catastrophe this planet has ever witnessed. And this miracle began with photosynthetic bacteria, whose sole purpose was to capture carbon. At the same time, they release oxygen as an unwanted byproduct. But there's a puzzling paradox hidden in this whole story. If photosynthesis produces oxygen, while respiration and decomposition consume this gas, then why does oxygen still accumulate in our atmosphere? Shouldn't everything be in perfect balance? And you're right, it should. In fact, most of the time, this balance is maintained. However, there's a significant loophole in the system's operation. A significant amount of organic carbon, a product of photosynthesis, is not completely decomposed. Instead of undergoing oxidation by bacteria or animals, it gets buried deep. This material settles at the bottom of the ocean and is gradually covered by layers of sediment, or is buried deep in places where decomposition cannot occur thoroughly. This buried carbon is the very carbon that photosynthesis captured along with the oxygen it released as a byproduct. However, that oxygen is never reused in the decomposition cycle because the carbon itself is never fully decomposed. This buried carbon, accumulated over hundreds of millions of years, is what we now call fossil fuels, coal, oil, and natural gas. This is organic carbon that once participated in photosynthesis, then was removed from the natural cycle, accumulating and transforming under the influence of pressure and extreme temperatures for millions of years. And when you burn a liter of gasoline or turn on a gas heater, you are releasing that precious carbon that has been deep underground for millions of years. And you are oxidizing it. You are combining that carbon with atmospheric oxygen to produce CO2. In other words, you are reversing, in just a blink of an eye, the delicate balance between carbon and oxygen, which took millions of years to form, is being rapidly released into the atmosphere by us. That's CO2 from ancient photosynthesis. And at the same time, we are breathing the very oxygen that was produced millions of years ago. The carbon and oxygen cycles are essentially two sides of the same coin. And fossil fuels? They are atmospheric oxygen, locked away as buried organic carbon waiting to be released. Currently, oxygen makes up 21% of our planet's atmosphere. This seemingly constant and eternal figure is in fact not. Throughout Earth's history, atmospheric oxygen levels have undergone astonishing fluctuations, not just over millions of years. For instance, during the Carboniferous period, around 300 million years ago, oxygen levels soared to approximately 30-35% of the atmosphere, a figure nearly double what it is today. The biological consequences, they appeared immediately. With more abundant oxygen, insects could reach enormous sizes. The limitations of their respiratory systems, which relied on passive oxygen diffusion, were lifted. Just imagine dragonflies with wingspans up to 70 centimeters and millipedes up to 2 meters long. A world of giant invertebrates could only exist thanks to that abundant oxygen. However, in other eras, oxygen levels plummeted dramatically to the point where modern animals would struggle to survive, periods that coincided with mass extinction events. An astonishing truth is gradually emerging. The amount of oxygen in the atmosphere is incredibly decreasing. The current 21% oxygen level is not a fixed number. It's a delicate dynamic equilibrium formed over millions of years. This balance is maintained by the constant interplay of photosynthesis, respiration, decomposition, and carbon burial. No physical law dictates that it must remain at that level. This number can fluctuate, and history has shown it has changed before. Alarmingly, the key factors shaping this oxygen level are precisely what we are currently impacting and altering. Whenever we talk about protecting Earth's oxygen supply, the conversation often revolves around forests. From protecting the Amazon rainforest to preventing deforestation. And while this holds deep significance for several entirely valid climatic and ecological reasons, however, if what you're truly concerned about is the atmospheric oxygen supply, then forests are not the key factor you might think. In reality, the primary determining factor is the ocean, specifically tiny plankton, namely Prochlorococcus and its relatives. The worrying thing is that ocean phytoplankton are facing impacts from changes we are creating in the ocean in ways many people are still unaware of. One of the consequences of ocean warming is a specific problem, stratification. According to physical principles, warm water is less dense than cold water. As the ocean surface warms, a layer of warm water forms, gently floating above the colder and denser water from the depths. The problem is these two layers cannot mix well. To survive, phytoplankton need light from the surface and abundant nutrients from below, that is, from the deep, mineral-rich waters. As this stratification increases, these essential nutrients from the depths will be unable to rise to the surface. In other words, phytoplankton in stratified waters are facing a true nutritional desert. Incredibly, despite being surrounded by water, there's a severe nutrient deficiency. This leads to a significant decline in phytoplankton, which in turn reduces photosynthesis in the ocean, and as a result, less oxygen is produced. Simultaneously, ocean acidification delivers another devastating blow to this ecosystem. The ocean, often called the Earth's giant green lung, absorbs CO2 from the atmosphere, and this very CO2, when dissolved, forms carbonic acid, which lowers the pH of seawater. Numerous marine organisms, particularly delicate phytoplankton, along with shelled or calcifying organisms, become incredibly vulnerable to this acidification. Their shells gradually erode in the increasingly acidic water, and their essential metabolic processes are severely disrupted. We are simultaneously and profoundly impacting, altering the temperature, chemical composition, and even the circulation patterns of the ocean. All these changes are directly threatening the very system that produces most of the essential oxygen for life on our planet. What's more, we are causing these severe consequences, yet most people are not even aware of the existence of this incredibly vital system. Take a deep breath right now. The oxygen that just filled your lungs was very likely produced somewhere deep in the ocean by some tiny phytoplankton, perhaps by the bacterium Prochlorococcus, hiding in the North Pacific, or perhaps a diatom drifting in the Atlantic, in the South, or even a cyanobacterium in some distant sea you'll probably never set foot in, created by a minuscule organism invisible to the naked eye, in a remote place you'll likely never visit, through a miraculous process by which life has persistently endured in the ocean for over 2 billion years. That tiny organism is completely oblivious to your existence. It doesn't produce oxygen for you. Instead, it expels oxygen as a waste product, an unwanted byproduct it needs to eliminate while performing its most vital task, absorbing carbon and reproducing. However, if it weren't for that waste, that byproduct of metabolism, from the invisible microorganisms floating in the ocean, there would be no atmosphere to breathe. There would be no animals. There would be nothing you recognize as complex life on this planet. The air you breathe doesn't come from trees. It comes from the ocean, and the ocean is changing.